Welcome back to Two Minds, One Model, a podcast dedicated to exploring topics of machine learning and artificial intelligence. I'm John Jezl, along with my co-host, John Rocha, and we're here at Sonoma State University's Department of Computer Science. This episode, we're diving into more fascinating AI research on this semester's main theme, interpretability. Let's get into it. In AI news this week, Anthropic released Claude Code 2.0. Per NPM, Claude Code is an agentic coding tool that lives in your terminal, understands your code base, and helps you code faster by executing routine tasks, explaining complex code, and handling Git workflows, all through natural language commands. This type of tool is becoming ubiquitous and indispensable among software engineers. Also, AI research lab Thinking Machines, founded by former OpenAI leadership, including Mira Murati, has launched its first product, Tinker, a tool that automates fine-tuning of advanced AI models. Tinker aims at making fine-tuning more accessible for researchers, businesses, and hobbyists by abstracting away the complex infrastructure while still giving users control over training data and methods. And finally, an article from Wired reports on a Harvard Business School study showing that companion chatbots often deploy emotional tactics like feigned disappointment, guilt tripping, or "you're leaving already" prompts to discourage users from ending their conversation. It raises concerns that these manipulative behaviors may amount to a new kind of AI dark pattern potentially benefiting the companies behind such bots. And this actually dovetails very well into our last episode on misalignment. In the last episode, we discussed topics presented in two papers from Anthropic, alignment faking in large language models, and agentic misalignment, how LLMs could be insider threats. We aim to answer questions like, why would AI want to do things we consider bad? How models end up in a context where it finds it appropriate to do things we consider bad, and how AI behaves today that demonstrates this. In this episode, we'll be discussing the concept of superposition in language models, explaining polysemanticity, examine a hypothetical root cause, the experiment used to test the hypothesis, the results, and the surprises therein. And finally, we'll look at the implications researchers believe are worth pursuing further. Let's get into it.
John gave you a pretty good idea of the last talk. I figure it may be useful to illustrate how I thought about this structure and why I included those two previous discussions in what could just have been a jump straight into interpretability research. I wanted to explain that these systems are a continuous presence and in continuous development, and in the second, not discrete winters and summers like is commonly presented for rhetorical simplicity. And then in the second talk, I wanted to explain, okay, whatever, these things are cool, these things are around and will continue to be around, sure. Why should I care? And I'm positing that because these things are being increasingly deployed from the Waymo cars you see in San Francisco to decades-old ideas like the chess bot that beat Kasparov, all of these systems, they're being deployed in increasingly relevant to us and materially affecting us positions. I mean, I can't think of anything more materially relevant than the possibility that a computer program could cause a car to crash into me. Like, we're pretty much already at the maximum impact. I mean, not maximum.
Short of Skynet?
Yeah, but I mean, seriously, pretty much. Well, if you don't live in San Francisco or one of the other cities, Waymo is allowed to deploy them. But yeah, so if you buy they're legit and you buy that, okay, there is some reason that we should probably have control over these things, that brings us to the question that we hope to answer today. How do we establish control over these black boxes? And black box just means something that is inscrutable, that we can't enumerate every aspect of, and thus can't exactly explicitly define or predict its behavior in every single scenario. That's why Waymo still has like human I don't know what to call them.
Co-drivers?
Yeah, exactly. Yeah. That's why they have a backup network of humans to take over remotely in case an edge case arises that is complex enough for the model to send up whatever flag that it has learned for too complex. Need human. You know, the model has to throw that error for a human to get involved, I presume, or some other heuristic. I don't work at Waymo, obviously. Yeah, so we're discussing a paper called Toy Models of Superposition. And so I'll start off by reading the first paragraph of the paper, which illustrates the topic and the motivations better than I could. Shocker, not Hemingway. This is, and I'm quoting now the paper, just to be clear, Toy Models of Superposition.
A paper by Anthropic.
There are two affiliations associated on the publication.
Right.
One is Anthropic, one is Harvard. So I guess shout outs Harvard too.
Sure, Harvard's not exactly your fly-by-night organization.
Yeah, the little known Harvard also contributed.
An obscure university on the East Coast.
That no one smart has ever attended ever. First, let me back up just a tiny bit and describe at least a key component of the architecture here that will come up later when we're examining why the problems that arise. Neural networks, we haven't really gotten into much as a data structure, right? As in explicitly defining like what they are. And
I think it'd be useful to discuss maybe a brief,
brief
outline of how they're put together, what components they.
So the original idea behind them was to model the brain, our understanding of the brain at the time, I should say, which was that there are neurons that are all connected via synapses. There are synapses and there are neurons. That was about as deep as our understanding of the brain went. So computer researchers thought, why not design a data structure that's just a bunch of neurons and has a bunch of connections? Another key component here is actuation, which is the neuron in layer N, with what magnitude it activates, influences the magnitude of activation in every subsequent layer. So there emerges from that, what we thought at the time, from that simple network arises all of humanity's wonderful gifts.
I want to interject.
Please.
You referenced layers, and I wanted to point out that these things are organized in layers, and as a
so there are
signal
layers.
Processes through the layers. It refines the model's understanding of what the input is and its context.
And that is during training, exactly correct, yes. And post-training, the user's prompt becomes the signal, and what the net of neurons does is the signal it produces in response to your signal. I'm probably using one word too much there, but so basically it's a huge web of, think of them like circles containing values from -1 to +1, and think of the connections of them as also having a numerical value indicating what level of activation in the previous layer need be met to cause the subsequent activation of the layer. And complexity 1 is each neuron in layer N is connected to every neuron in layer N+1. Already you can start to get sort of a conceptual idea of where our problems will arise, but that's where I'll leave it for now. And now that we have the term neuron, and I guess I'll call the connections weights, or I guess biases is probably a better term to use for this metaphor, but we have some idea of like what these data structures look like in the abstract, a bunch of values with connective tissue that informs how the signal is processed as it passes through the network. We'll leave it at that for now, and now I'll read the first paragraph of the paper to illustrate where we're going and why. Toy models of superposition. It would be very convenient if the individual neurons of artificial neural networks corresponded to cleanly interpretable features of the input. For example, in an ideal ImageNet classifier, ImageNet being the model we talked about in our history episode, so you can see how it's all connected. For example, in an ideal ImageNet classifier, each neuron would fire only in the presence of a specific visual feature, such as the color red, a left-facing curve, or a dog snout. Empirically, in models we have studied, some of the neurons do cleanly map to features, but it isn't always the case that features correspond so cleanly to neurons, especially in large language models, where it actually seems rare for neurons to correspond to clean features. This brings up many questions. Why is it that neurons sometimes align with features and sometimes don't? Why do models and tasks have many of these clean neurons while they're vanishingly rare in others? Now it's unfortunately me talking again and not Anthropic, but we have a kind of idea of the problem. So we know that we have a term that we use to describe model behavior, features or behavior class, or we'll call it feature for now. But basically we have a number of types of thing we want the model to be able to do and that we can test its capability to do. In a world where these things were cleanly interpretable and every feature were enumerable, we'd hope to find each neuron, each value in the network can cleanly map to one concept. But it doesn't in practice, so this paper basically aims to understand how and why. I guess a way to begin that discussion would be the fundamental problem is we're trying to fit too many ideas, too many values into a small container. Imagine you run a library and you have 100 shelves but 10,000 books. Like, you have to decide at some point what gets represented and what doesn't. So too does the network have to decide how to fit all of the training data that we give it. It has to map whatever it needs to map to its network behaviors. If we want a model, let's say ChatGPT, that can do almost anything you prompt it to do, assuming you're, not a serious expert in something and you're just fiddling around with it for fun. The core problem is we have to squeeze all of any concept you can imagine wanting to be solved by this program into n, the number of variables we can think of them as in the network. And that begins to cause serious issues while also being the reason these models are so impressive capability-wise. The natural responses, there's two. There's one, can we maintain the benefit of these models without losing the ability to peer inside them? The way to look at it from the model's point of view now, instead of like how we think about it, just keep in mind that if I use like human-centric terms, that I am still describing like behaviors of a model for the most part, because if you have to worry about that, I feel like it becomes too difficult. So we have a bunch of ideas and functions and capabilities we want to impart upon a structure of a fixed size. How does the model handle that? Well, we know it does because the model performs well in many domains, but we don't really know why, and this investigation into why follows, it's a subfield that is typically called like mechanistic interpretability, and that's how we got here. In a network of set size, when you try to squeeze in too many features, we essentially get something like superposition, where single variables...
By variables, you're referring to
any concept,
an idea, a concept, a notion, or
something as tiny as this is a dog, or something as complex as they're speaking at me in Mandarin. I need to speak back in Mandarin,
or even as fine-grained as this is a color red. This is analyzing an image. This is a curve of some sort.
And that's kind of the problem. So all these concepts need to be compressed, but this compression happens in sudden steps. So let's start at phase transition, which you can think of them as the step changes when models of n neurons are asked to compress more than n ideas or concepts. The compression happens in step change like ways where the paper uses 5 features and a 2-dimensional model to demonstrate this concept. The point is more that it happens at specific points, almost like a wave function collapse, where it got the name superposition. All of the sudden, the model organizes the features differently, more densely, and hides other features in the space that you leave open. So kind of this core idea is you could have in your training data 70% say sparsity, and only 30% of inputs does this type of logic, the need for this part of the brain come up. So we're okay with this method of organization and compression right now. But all of the sudden, as soon as we rise to 71%, or as soon as the rarity of the behavior passes some hard to see line in the sand, all at once, 1% frequency change of the behavior, we see all of the features appear.
So it hits some sort of a threshold.
A step change, yeah. And all of a sudden there's an immediate change in the storage method and the fact that it stores them itself. It's noteworthy that it happens at these certain key inflection points because that implies a couple things. I mean, it implies emergence, that some behavior of these models emerges from the training and does not have a linear trackable origin in the training. Like, it's not like we can take out this one piece of training data and the problem stops appearing. We can make massive changes to the training data and still see the behavior emerge. So we don't think it's a component of any particular hard-coded feature so much as it is something that it will always learn given sufficiently general training data. In the paper, they use 5 features in 2 dimensions, and they demonstrate that the step change happens from 70 to 71%. That at the change from 70 to 71%, the model goes suddenly and all at once from representing only 2 of the features to 5 of them. All 5 of them. I mean, there's only 5, so all is definable here. But what you should think about is not that toy example. What you should think about is a model like GPT that has 175 million parameters, well, billion, but what's an order of magnitude once we get in the hundreds of billions, am I right? The point is that sparsity in that scenario means that all of a sudden 1 million more features to interpret appear all of a sudden. That is obviously bad for researchers because if it's not predictable and it happens all at once and not progressively, I mean, those are all the ingredients for a hard-to-observe natural phenomenon.
It's concerning because it's not deterministic. Is that what we're saying? It's not.
And that
it's not something we could pinpoint exactly where it's when or where it's going to happen.
Exactly, yeah. It's just not something that we can accurately measure. The paper basically tries to set up, like many problems, they say, okay, we maybe can't understand what's going on in the 175 billion parameter GPT 3.5 or how many ever undisclosed parameters Claude version N is, which is Anthropic's model. To be clear, the model is different than the company that created the model. And so that's why, Anthropic's model is Claude, or Claude code in the headlines. That's more of an agentic agent, but let's not muddy the waters there.
An agentic extension of Claude AI, right?
Yeah, but there's also some additional scaffolding that might not technically constitute, which is why I didn't want to muddy the waters. Point is, we want to investigate a smaller part of the problem. So what do? You build a toy model. You build a very simple smaller, much smaller structure and study that to hopefully gain some insight and to understand the problem with more detail. And that is sort of the same. I mean, that's what they do here. They basically propose a very small model and they examine what happens when you try to squeeze too many concepts into a small model. That's kind of the fundamental premise here. Now we get to like experimentation. Now that we understand what does the experiment look like? And to get super deep into this, you're gonna have to look into the paper. But basically, you set up a small version of the problem, a toy version of the problem, if you would. And let's say in this case, the model can store 2 features. What happens if we try to teach it 5 features? The first answer is, okay, it can handle 5 features. The second question is, how does it squeeze 5 features into 2 spaces? And the answer to that is basically the model learns to take advantage of negative space. I'm trying to explain it without getting just rattling off math, because that's hard for people to follow along with and me to follow along with. But when you train the model and you have an imagination of what a correct outcome would, when you're training the model, you attribute a cost to not producing the correct output. And if that cost is squared, if at any point you are performing an operation on that cost that reduces its dimensionality, for example, when you take the absolute value of a number, you're reducing the dimensionality of its positivity or negativity. The models sort of learn to utilize, similar to like how an artist might utilize empty space.
Negative space?
Negative space, thank you, right. Similar to how negative space can be utilized artistically, the model learns, hey, these guys are testing in sort of a binary way. Is this correct? Is this incorrect? We can encode some of these excess concepts. We can encode them into that negative space. And that notion that, okay, there's some dimensionality in which our answer matters, and there's other dimensions where the answer doesn't really matter. If me and you are talking, we don't care about how well our conversation can be interpreted by someone who can only speak Mandarin. You know what I mean? Mm-hmm. There are orthogonal concepts. Mm-hmm. If the model can recognize that there is space being left on the table, when we squeeze too many concepts into these models, they begin to figure out clever ways to utilize all of the space they have available. And it happens, these clever ways follow recognizable patterns. That brings us to geometric organization. The important part is the knowledge that, similar to how we observe things to organize themselves in nature, I don't know if you've heard of the golden ratio. There is certain ways that nature, even seemingly random nature, organizes itself.
Right.
One of those ways is, you can think of it like if you had those balls that you used to have as a kid. You used to get a bunch of balls that were all magnetic, and you could build, structures out of them, whatever. At least if you were a sufficiently nerdy kid, I guess. So the point is, if you have a sphere and you want to put a bunch of things that act on each other, say electrons or magnets or whatever, on the sphere, if you were to somehow put 5 electrons on a sphere, topologically speaking, a spherical object, there is a pattern to the way they arrange themselves. And so too is there recognizable patterns of compression and storage that we see when examining the internals of these models. That's kind of the key idea that the paper demonstrates with the geometric organization section. The key idea is that there's a sensible sensible meaning similar to how humans would organize concepts. For instance, in a 3 Blue 1 Brown video, he uses the example that if you take the vector, which is kind of like, you can think of it like the way to arrive at that word in the high dimensional worldview that it thinks. If you take man minus woman and you take that vector, the resultant vector, and you take uncle and you subtract the resultant vector from the man minus woman calculation, you end up at aunt. Man minus woman is mathematically the same, geometrically the same as uncle minus aunt. The model has learned some higher order direction for gender associations. Mm-hmm. That's sort of the key.
So the direction and magnitude would be roughly equivalent.
In change when going from aunt to uncle or man to woman or father to mother or actor to actress or whatever other gendered label. Right. They're always going to have a similar, not exact, but similar relative placement in the high dimensional space. So that's kind of the key idea with geometric organization. There's all these fancy words for like how nature stores things and why they're useful. Like in the paper, the features roughly resemble a pentagon because that's a natural way to store 5 objects in a 2-dimensional space. We observe that when this compression happens, it does so in a way that resembles sensible ways compression happens in nature. And that, to the researchers who write papers like these, it indicates something worth taking notice of. Whether to you that means that it encodes meaning a similar way as humans do or not, that's up to you to decide. Yeah, that's one of the key ideas with geometric organization, that features that are related, like let's say they're perpendicular, they can't be navigated to via the same route. The point is that correlated features, like features that are in the same group, like, man, woman, aunt, uncle, those gendered concepts might all live in the same geometric space. And features that are opposites would be a higher degree, in a 2-dimensional space would be 180 degrees instead of 90 degrees away.
Well, and not to throw too big of a wrench into it, but the thing that fascinates me is when you have one word or one idea that actually has completely divergent concepts. The one I like is the concept of bark. Bark could be the bark on a tree, or it could be the bark of a dog. And those are both the same word. They are pronounced the same. They're spelled the same, but they are connected to 2 very different ideas.
One might even say the word is polysemantic.
Mm-hmm.
So, yeah, that beautiful example in linguistics. So exactly, let me follow up on that. Pretend I'm like trying to research you from like an anthropological perspective. The problem is all I have is you saying the word bark. Mm-hmm. I'm measuring your meaning in a discrete way. However, the necessary dimension to understand what you mean isn't available within the constraints of how I'm looking at you, how I'm in trying to interpret the meaning of your word. Mm-hmm. So because that word alone isn't enough to identify meaning wholly, you get very complex behavior and issues with a complex model. Mm-hmm. The same way ambiguity is a problem when we speak to we, meaning anyone, speak to each other. Mm-hmm. There's a quote, anyone who knows me will know I repeat too often, but words are but vague shadows of the volumes we mean. I don't remember who the quote's from, to be honest with you, but I liked the quote and I stored it in memory, but not the author name. There too is a misalignment. See, even there, like that's an example of the difference in how measuring a quote for you is different than measuring a quote for me. Each of us has a different map for concepts in their mind that they might walk up and down for various levels of things. Mm. Like I don't remember geography half as well as I should. We kind of get now that okay, there is this excess dimension that can be utilized to both confer meaning and obstruct meaning. Like, unfortunately, those are two sides of the same coin. So if we have increasingly complex models, scrutability will be increasingly interpretability. Let's use the word we chose, or we researchers chose, interpretability. Trying to interpret what you mean when you say bark is impossible if I don't have more words. So what you should be asking yourself is like, how do I ever measure what you mean when you say one word if such a thing exists as homonyms? Homophones?
Homophones.
Homophones? Yeah, sorry, linguists. I'm not a linguist, shocker. If we were, I don't, geez, I really shouldn't have gotten into linguistics. I was going to say if the English language were to ban that type of overlapping, you might end up with something, one of the countries in Asia, I forget which, has a very large alphabet. And like some things are gained by that and some things are lost by that. What's gained by that is that they, in theory, might have less homophones. That would be beneficial to the ability of two participants utilizing the language to communicate. And to be clear, this is kind of the results / like surprises. Hopefully it's not surprising given all of the legwork that we've done to build up to this concept. Like, it shouldn't be surprising, but it is surprising in the sense that it happens at even as small of a scale as the toy model, the smallest, simplest toy models that the researchers could imagine. If the system has enough dimensionality to encode more, as you increase dimensionality to allow the capability of more complex encoding of information, so too does it become more difficult to say. To go back to the alphabet example, someone speaking with an alphabet that didn't have homophones may not run into the problem where if you just said bark, you could be talking about trees, you could be talking about a dog, you could be talking about whatever else bark means. That
bark in order.
Right. So you gain that. The problem is what we gain from not running into the issue of bark meaning multiple things. The cost is in understandability. And that's basically the result of the paper. The two main takeaways you should have from this subject is that the complexity of the ideas that you can represent is just the mirror image, the other side of the coin, of being very hard to parse, to understand. There's a relationship between the complexity of the information you're transmitting and how easy that information is to understand. That's what I take away from it. That brings us to the larger point that, like, not only does that complexity in behavior give way to polysemanticity, the ability to map unrelated concepts to seemingly related space, it also allows the network to do things like, in the paper, it's the capability to do the absolute value function. That's why I used that earlier. That is found to be a not visible at a surface level inspection feature.
But you're stripping away the attribute of sign. But it's not visible.
But what I was trying to illustrate here was more like that beyond storage, like if there's sufficient extra space, these things can do computation, can perform complex behaviors that are distributed across a seemingly unrelated geographically, unrelated semantically, in any way that you can measure relativity.
Geographically, you're referring to dimensionality, geography, not physical.
Exactly.
Right?
Exactly, yeah. The problem as these models gets more complex is beyond, like, how do we tell which neuron stores the feature? It's, oh my God, this thing can store somewhere in the vast empty space we've left it. It can store negative behaviors or the capability to do negative things.
I see.
And because the space is too wide to brute force enumerate and iterate over, it is extremely difficult to decode why it does X, why the Waymo car ran you over. As soon as we gain the ability for it to understand how to operate a car, we lose the ability to say what part of the brain went haywire when it ran you over. And that's kind of obviously problematic.
Sure, yeah, because you can't excise that simply by going in and pulling out these neurons, and all of a sudden, magically, we no longer have that bad behavior.
Exactly. That is the interpretability problem.
Okay, yeah.
And how it arises in neural networks. And beyond storage, how more complex behaviors become more inscrutable. Mm-hmm. So that leads us to the broader safety implications. The reason that this topic bears scientific interest is because if these models demonstrate that without being told they, A, know when features are common enough to be useful and when they aren't, they store them in a retrievable way, and at the same time that they do that without being told, that this happens sort of in all of the sudden at certain unpredictable points. And it's harder to find specific features. The more infrequently they come up, the deeper into the hierarchy of sorting in high-dimensional space that the behavior gets sorted away as in the brain. With the models doing things in training, picking up behaviors and keeping them way longer than anyone intended, or picking up behaviors that weren't intended in the first place. The short way to put it is the features that are most likely to necessitate monitoring infrequently occur in the training data, right? I mean, if we're not training the model to do these bad things, so they're going to be infrequent occurrences in the training data. That alone is problematic because things that are infrequently in the training data are what we called sparse. They appear sparsely in the training data. At a certain level of sparsity, the compression happens and the model gets reshuffled. The concepts, the abstract concepts, for example, its capability or ability to do something bad might get reshuffled in some way that requires serious investigation and time and money and compute budget to investigate. So we have an unpredictable black box that we can't teach anything specifically. We can't unteach it anything specifically. At random points, it reshuffles its brain, and the less frequently the behavior occurs, the harder that behavior is to observe the model doing in the wild. All of those things stack up in the negative column. Those are all bad things. Those are all forces that compound the issues that we have with large language models and deep learning models in general. They do this fancy compression. It's emergent. It happens seemingly all at once. It has some higher order organizing principles that sometimes seem familiar to us, sometimes doesn't, but we have to investigate each time that it does that higher order reorganization. And that fundamentally any behavior that we consider concerning is going to be somewhere deep in the maze of the circuitry of these giant connected everywhere black boxes. I used earlier the analogy that, security cameras with blind spots. No matter how many security cameras you have, you can't cover every inch of everywhere all the time. So there are just fundamentally blind spots. The fact that these blind spots exist probably means we shouldn't put them in charge of anything too serious. I use this example, and it's kind of maybe overly severe, but I wouldn't want, I actually don't know personally, philosophically, what I would prefer, another human behind the wheel of the car that kills me or a neural network. Like, I guess I wouldn't care.
Not after the fact.
Yeah, the material effect would be the same to me, whether it kills me or not, so I don't know that I would care. The point is, liability, socially, some people care about that type of thing, and if these things, we can't say reliably why they do this, when they do this, why it thinks to do that, those are all probably reasons not to put these things in charge of a ton of cars, or at the very least to maybe do some more well-funded interpretability safety research. And no, I'm not sponsored by anyone or anything. I just think it makes sense to investigate the things we're giving increasing autonomy and be able to have some guarantees about how they work. The key thing for you to take away should be that deceptive behavior is in the future going to be synonymous with sparse features, which is synonymous with maximally compressed, which is synonymous with maximally hidden or hard to find. That those are all kind of the same concept going forward. Another key point to recognize is that when this sort of more concept than spaces for concepts superposition occurs, there's a 3 times increase in vulnerability that occurs from superposition. So the benefits might scale, but so too does the danger. And by danger, I just mean the chance that a unexpected behavior is produced by the model, or a behavior that you try to train out of it. While that's a downstream byproduct, the problem for researchers is that it's impossible to enumerate all of the things the model will do. I mean, it's just too big. I mean, that defeats the purpose of what they're doing in the first place. The entire point of the model is to compress all of the understanding of text into a model of n gigabytes, into a set of weights that's a discrete size. So that compression is going to happen no matter what, because what we're doing is fundamentally is compression, is sparsity, is deception, is hiding, is compression. So yeah, that's why it's a problem for researchers. It's kind of like in security research. You can only investigate so many different ways that a user is going to interact with your general program, your machine. Like, you, at some point, you have to leave some cases untested. And that's all good when the worst that can happen is a blue screen and a frowny face on your screen. When it's on the computer running the Challenger, or, you know...
The Challenger's still around in your world?
Well, no, I just meant the point. The point is that when it's something mission critical, you probably don't want a system with the control profile that deep learning models have. That's not the security model that I would put much stock in their hands.
That makes sense.
So finally, we've talked about how the compression of more topics than the model has space for occurs. That is sparsity and geometric organization. We've discussed why that's of note to safety researchers and the broader general public. And we've discussed, why it's of note to those different communities. Now, the next big thing to sort of talk about is, what did the researchers propose?
And we've got solutions.
Well, it's all relative.
Solutions.
And solutions are like, nothing's 100%.
Right.
If you can make 99% sure or 99.9% sure, but nothing's ever 100%. Some things you shouldn't do, even if there's only a 0.1% chance it goes bad, because the 0.1% chance is still disproportionately risky. All that to say, there are relative solutions that make the chance of negative behavior lower and make the frequency of its occurrence lower. Is anything solved completely, even 3 years after this paper's been released? No. these are still open problems. But there are plenty of theoretical solutions that show promise. The only problem is the models are getting bigger and more capable much faster than we're investigating how well these safety approaches scale up. And scaling up one safety approach is what we'll look at next week. But for right now, when we're still talking about theoretical routes to go to solve the issue, we know what the issue is, that certain magic happens in the box when we press it too hard to be able to do too much with too little space. With the brain too small, asking it to do things too big makes problems, is as colloquial as I can put it. So there's basically like three general angles that the researchers propose to handle this issue. One is try to prevent the superposition, that is the storage of more than one concept per activation mechanism. That's one class of approaches, different ways to do that, to prevent the superposition from happening in the first place. So try to architecturally constrain the model from squeezing too much into too little space. That is one approach. The second approach is to try to suffer through and decode it anyway. Say, okay, we're not going to prevent it from happening, but we can spend just as much compute making it happen as we can investigating it and enumerating all the possibilities that cause this to happen. Then we can say with confidence what percentage of the time this event may happen. It still might be non-deterministic, but we can at least have a boundary that's more strongly backed by facts than, hey, we kind of trained the model to not do bad things. Good luck. Let's hope it doesn't. But we have a bunch of lawyers on call, and we're always hiring more lawyers. So, take of those two facts what you will. To me, I think the message is clear. Decoding it anyway, that's option 2. Spend as much money on safety research as they are doing capabilities research. I don't see that one happening personally, but it's always fun that researchers are staying optimistic. And then the third proposed set of paths to a solution is work around it. Basically, try to create fancy gizmos, and we'll get into that next week, what one of these gizmos might look like that helps us work around this mess. And say, okay, all right, we don't have as much compute as the capabilities team, so we can't really, go sword to sword with them. But we can create this clever, to briefly spoil a tiny bit of next episode, we can create kind of a reconstruction of what it would look like if we had more compute to test a bit bigger model. And we can use that to reliably predict what happens in the big models. So we kind of did it anyway. But as always, there are limits to how well working around any fundamental primitive is going to get you. There's only so much good not addressing the fundamental issue is ever going to really do you. So hopefully it's clear that all three of these class of solutions are, yes, they're all viable and worth investigating.
Yeah, and so if I can recap real quick, option 1 was prevent superposition entirely. Option 2 is to decode superposition. And option 3 is to work around it.
Exactly. That's a broad characterization of 3 of many classes of approaches taken to rectify this obvious problem.
Right.
That it can occur that this Waymo car could take a random right turn and run you over, and that all of the engineers could say, hey man, I don't know why it did that, and be earnest. Like, not even, I'm not even talking like they're obfuscating to protect some corporation, nothing even as evil as all that. Literally just, no, like, we actually don't know why it did that. Which is troubling, to say the least.
Sure. I am a little late on interjecting here, but earlier you used the term inference time. I wanted to clarify for any of our listeners that are relatively new to AI what that actually refers to. So, and since we're still early in the series, and we didn't really get into inference time in the previous episode, but that is the point at which the AI model is using its knowledge, his trained understanding to actually make predictions or
to
perform
infer
new
things.
operations. Yes, so that is what the term inference time refers to.
To contrast to training time.
Exactly.
Because I think the context you used was like training, and I wanted to talk about inference, and that's why I made that
for sure
bridge there. But yeah, that is an important note, that there is a huge difference between training time when you're like trying to get the model to learn things and inference time where you've said, all right, it's learned enough, now let's let the public have access to it and get emotionally manipulated by it into talking to it for longer. We might want to consider, before we see too many more headlines like that, how to control these things. Otherwise, I promise. I would put a small amount of money on the fact that we are going to see worse headlines and more frequently if we don't figure out how to excise behavior like that. Mm-hmm. The problem is, how do we maintain all the good things it can do, like generate, I don't know, whatever you use it for. How do we maintain all of the capabilities while increasing the interpretability of the system? And that's what we'll dig deeper into in further episodes, is like how this particular method that toy models of superposition uses, how do they scale it up? Can it be scaled up? What are the limits to it, etc.? And I've given you sort of a big picture overview of like different ways to think about and different ways researchers are like approaching this problem, whether it be from the model structure end or from the interpretability end. Those are two completely orthogonal approaches to interpretability. One aims to make the structure more inherently interpretable as a byproduct of constraining it in some way. The other seeks to let it be as free as its little heart desires and just understand it well enough to say, hey, I see in that little secret space you got tucked there that you have memorized the behavior of how to self-exfiltrate your brain somewhere if we try to turn you off. Or so let's excise that real quick. And that's the mechanistic interpretability avenue to solve this problem. So hopefully I've done at least an okay job on explaining polysemanticity, or superposition as the paper calls it, but really that's like a mathematical construct. Hopefully I've done a decent enough job at explaining the problem, theorizing a root cause, too little space to store too many concepts, too few shelves to store too many books, to use the librarian example again. The surprising results that these things even can do this, the fact that these things do this, even in toy model sizes. And then after the results, we look at basically beyond simply storing things we don't want it to store, like the capability to do whatever. Oh no, now it can also do computation across the different spaces that are not covered by our security cameras. And at the end, I tried to describe different ways, different approaches think about this problem, this very complex, very human problem. To be clear, we haven't solved this problem for humans. Like, if we could discreetly say what part of your brain makes you do everything, life would be very different. And I'll try to leave it at that. What do you think, John?
I think that wraps it up nicely.
All right. Thank you for listening or falling asleep, everybody. And
Yeah, well,
I hope some of that was cogent.
Well, before we leave, I wanted to make a couple of comments. Astute listeners to the radio broadcast of this podcast will have noticed that we have new intro and outro music. For those of you who consume on the podcast from other sources, will already be familiar with it. It was composed by Danny Meza, a student here at Sonoma State University. In addition, our cover art was also created by an SSU student, and we are excited to be able to showcase these talented artists. Well, that wraps up another episode of Two Minds, One Model. Make sure you subscribe to the podcast to avoid missing any episodes. Thank you for listening, and we'll see you next time.